It sounded like he's a giant.
By chance. Oh, it says I only have one. Here, I don't use it. I don't use it.
Military sound.
All right, everybody.
He will serve his country well.
Okay, now remember that these can be rewritten. This is our translational equation. Here's rotational. Okay, remember with translational, all we're concerned about is center of mass. That's it. We don't care about anything else. Here, the shape of the object matters, okay? Okay, so center of mass only for translational. For rotational objects, the shape of the object makes a difference. Okay? And where the forces are located makes a difference. Okay? All right. Now remember, we can rewrite this. Actually, the more precise way to write this, if you remember that F equals ma assumes that mass remains constant, right? And that's not always the best assumption. So if we rewrite this, we can write this as what? F dt impulse equals the change in momentum, right? Or if you prefer, there's like a billion different ways to write this, right? But this, remember, is j on this side. That's a vector, that's a vector, that's a vector, that's a vector. Got a vector here, got a vector there. Okay, vectors all over the dang place. Okay, they're vector equations. What? I said vectors all over the dang place. What do you think I said? All right, now. All right, sum of the torques dt vector equals change in angular momentum. Okay? We've talked about angular momentum already, right? What's angular momentum?
IW.
I omega, or change in R cross MV, right? Okay, whether you have a continuous size or a continuous mass object, you use this, like a disc or a sphere, some shape, and this if you have a lumpy mass object, just discrete pieces of mass connected somehow or another by magical massless thingies. Okay? Wow. All right, now, here's the deal. If we want to have conservation of momentum, which we talked about, what must be true? Which means this, which is conservation of momentum. What has to be true for this to be true?
The net outside force has to be zero.
This, the net outside impulse, this has to equal 0, and then you get this, right? But net outside impulse, or net outside force, essentially, right? That's the key. No net outside forces. No outside forces of any meaningfulness, right? So like in a car collision, we have to talk about right before the collision to right after the collision, because there's some friction between the tires and the road, but we can generally neglect that as long as the time period's not too great, right? Okay, or if there's no net outside forces. It's all nice. Okay, well we got to keep track of all the objects. Okay, over here, if we want to have conservation of angular momentum, what must be true?
Net torque.
That must be 0, right? That means there can't be any net torque. All right? Okay.
Does that have a fancy name?
Oh, you know what? I don't know. Angular impulse. There you go. I made it up. Actually, I don't know. There may be a name for that. Whatever. Angular impulse. There you go. Yes.
I'll see it rotational if it's not torque.
Well, that's a good question. How can you have any rotational behavior if there's no torque?
You said this last class. I knew it.
It's already
Yeah, so how can you have any momentum without an impulse? Yeah, it's already moving. Somehow or another, there has to be something that had gotten it going, right? But then you're just talking about the interaction afterwards, okay? So that's a good question because that comes up a lot. We're just talking about, we pick the time that we're looking at, right? So we pick the time after it's already moving, and then we look at the behavior, okay? All right, so there you go, no outside torques. Now, we're going to find out that that turns out to be kind of interesting because, look, is it possible to have an outside force that will mess up conservation of momentum, but you don't have an outside torque?
If it's on the axis, right?
And the key thing is it possible to have a torque without, is it possible to have a force but not have a torque?
Yes.
What's the condition?
It's on the axis.
Okay. The deal is that if this is your pivot point, you got an object right here, that's your pivot point. So there's lots of places that you can apply this force and not get a torque.
Lots.
Sure.
Yeah. Oh, this way.
You could apply force that way, or that way, or that way, or this way, or that way, or this way, or that way, or this way, or this way, right? As long as the effective radius is 0, right? Does that make sense?
Yeah.
Okay. So if there's a force that acts through the center of rotation, then we can still have angular momentum conservation. Okay? All right, so, oops, I erased something. We might need someday. Well, here, I bet we can figure that out. All right, let me start with an easier problem. I've got kind of a hard problem here. Let's start off with an easier problem.
Since most of the class was in here.
Most of the class wasn't here.
Yeah.
Oh.
We decided to go on a field trip.
Field trip.
Why they needed to go to a field, I don't know.
Yeah, trip to a field. Sounds very educational. All right, so let's do this. Okay, let's say we have a rotating disc. Okay? The moment of inertia of this disc is 3 kg-meters squared. The angular velocity of it is 12 rads per second squared. You're going to drop this onto another one.
Yes.
Sorry, rads per second. Thank you. You're going to drop this onto another one.
Whoa.
Both of them free to rotate. Okay?
I think we
The moment of inertia of this one is 6 kg-meters squared with an initial angular velocity of 0.
So are we assuming they instantly stick to each other?
It makes no difference.
Oh no.
And here's why. Okay? Now that's an excellent question. The question is do we assume that when they hit, they instantly stick? Or whether they kind of slide or grind past each other until they go the same speed, right? The answer is that it doesn't matter. Okay? Just like if we have a car collision and they collide, and whether they have nice big spongy bumpers or whether they don't, makes no difference in the fact that the momentum before and the momentum after will be conserved. And the reason why is the big spongy bumper, what will it change? It will change, very good, force versus time. If you have a rigid bumper, you'll have something like that. If you have a spongy bumper, the collision will start at the same time, but the collision will last much longer, okay? But the deal is that the impulse on the two cars actually come in a pair. They usually only show you the one, okay? But one is to the right and one is to the left, and these two pairs are equal but opposite, right? Same time, same amount of force, same net impulse. One positive impulse, one a negative impulse, just like we have here. When these two collide and they apply a torque to each other, notice the top one is going to apply a torque which way? Which way is the torque? It's going to be this way, right? Upward.
Yes.
Whoa. An upward angular impulse.
Yes.
And the bottom one is going to apply an angular impulse to the top one. Which way? Downward. This way. Through friction. Now, whether there's friction or Velcro or whatever in between these two, it doesn't change the fact that they're going to apply equal and opposite impulses on each other. Angular impulses. Okay? It just changes the time over which this will occur. Okay? So the time, it won't make any difference. So the key thing is that from beginning before to after is going to be the same exact result, as long as they both end up moving the same speed. So we're going to end up with a completely inelastic rotational collision. Did you get that?
Yeah.
What does that mean?
They stick.
Yeah, they stick. Completely inelastic rotational collision. They stick. Will kinetic energy be conserved?
No.
We're going to lose some rotational kinetic energy, right? In a completely inelastic rotational collision. Okay?
Bro, if that bottom thing was frictionless, it wouldn't.
Oh, the top one to fall on it and just keep sliding. This way. Nothing.
Because it's still conserved. Just
Right.
not an exciting
Right.
outcome.
Now, I got a question for you. This thing has to be sitting on something or keeping it from falling, right? So this one is on something, some kind of spindle or something. So the deal is linear momentum conserved? When the top one hits the bottom one, is the bottom one free to move?
No.
No, there's an outside force down here keeping this thing from moving, right? So we do not have this, right? We do not have conservation of linear momentum. But we have conservation of angular momentum because there's no outside torque if it's free to spin. Does that make sense?
Yeah.
Okay, here's another reason. The outside force holding this thing up is coming from the ground upward, right? And our pivot axis is right here, right? Notice that the force does not produce any torque, right? So since there's no outside torque, since it's free to rotate, then you have conservation of angular momentum. Now after all this gobbledygook of talk, let's solve it, and you'll find out it's quite simple. Okay, since there's no outside torques, conservation of angular momentum must be true. So therefore, how much angular momentum do we start with? Okay. Okay, do we use R cross MV, or do we use I omega? I omega, because that's what's given, right? It's nice and easy. So we have an I omega for the top one, plus an I omega for the bottom one. Okay? Plus an But beforehand, the bottom one's not moving, right? So this is 0. So we just have the top one. That's it. Okay, afterwards, we have an I omega for both, right?
Yes.
Or do we combine them? Can we combine them?
Yes.
Will they end up with the same omega?
Yes.
So we can have I of the disk plus I for the fatter one times the same omega, right? The final omega. You notice this is exactly like a car collision, right? Where you have MV plus MV before equals M plus MV at the end. Because they're stuck. Right? So it's the exact same thing. So, piece of cake. So what we have is 3 times 12 equals 3 plus 6 times omega final. So what's our omega final? 4. 4 rads per second. Voila, done. Okay? Okay, how many of you have a car with a clutch? Or a driven one? Okay?
Driven.
All right, those of you with a car with a clutch, you do essentially this. Okay? When you push in the clutch, you separate the 2 rotating plates. Okay? And then when you let the clutch out, the 2 plates come together. One of them is driven by the engine. One is attached to your wheels, essentially, directly. Okay? All right, so the engine's spinning, and then you let this plate connect with this plate, and they squeeze together, and eventually they'll both rotate the same speed. Now your engine is directly connected to your wheels. Okay? But when you let out the clutch, what happens to your RPMs? They go down. Because you just connected a big non-rotating mass to your rotating mass, right? And so the whole thing slows down. And so you have to give it the gas, or otherwise you're going to kill the engine, right?
But sometimes you do anyway.
Sometimes you do anyway, right? So there we go. So let's go on to something a little bit more substantial. How about we do this one? This one's always a fun one. We have a person standing in the middle of a merry-go-round. Okay?
That's never the best idea.
Oh, no.
Actually, it is very fun. Until you fall off.
Why has it got to be a girl? Because she likes the merry-go-round.
She's hanging in the middle of it.
Merry-go-rounds aren't massive.
Why does that have to be a girl? Because it's my daughter, because she likes merry-go-round. So there. Oh.
Do you remember the little thingy-majiggers on playgrounds where you like run and then you jump on and you like try laying down or
Those
like
are
do
fun.
something like that?
Yeah, they took them off because they're not safe anymore.
They're not safe.
Oh,
They're
that
not
thing's
safe at all.
Isn't that a merry-go-round?
They're fun.
Yeah.
Oh, that's what they're. But it doesn't have horses.
Yeah.
Yeah, it doesn't have horses or anything.
No. All the merry-go-round is a big disc with a few handles, a few safety bars, just so they don't get sued.
So you break your
That wasn't in
teeth.
my playground.
Yes, that's right. So you have a nice piece of metal to break your teeth on as you're spinning around.
Another cushion with pillows.
That's right. A cushion with
I like the
pillows.
ones that have them like this, so like you go really fast and they clean
All right.
so you won't fall off.
So the mass of the girl is 50 kilograms. The mass of the merry-go-round. Merry-go-round.
I thought your daughter was very small.
I was about to say, this isn't your daughter, is it?
What are you implying? That my
Oh my gosh! No!
You're implying that my daughter is a spheroid?
He jumped on the bear.
And then falls on his head.
I'm making the math
We
simple.
covered it in Mark Square.
All right.
Oh,
All right, so here we go. The young lady is standing at the very center of the merry-go-round. The merry-go-round and her have an initial angular velocity of 2 rads per second. The girl walks to the rim from the center. So she walks straight out to the rim of the merry-go-round. First of all, when that happens,
What's the radius?
the radius, oh, good question. The radius is 2 meters. Okay?
So it's changing.
And we will assume this to be a disk. Okay? We will assume the girl to be a point mass.
It's not a hoop. She's not in a hoop.
She's not a hoop. No, she's not standing in a hoop because she'd fall on the ground. All right. So the question is, my first question is, if she walks to the rim, is she going to accomplish that without killing herself? Okay?
Fly off.
And she walks to one of these things so she doesn't fly off. Now, what will happen?
It'll slow
It'll
down.
change the eye.
Why? It'll change the moment of inertia. The moment of inertia goes up or down? Up. So what happens to the... It says it slows down. Why?
Because I omega stays the same.
Because if... Wait a minute. Will angular momentum be conserved?
Yes.
Are there any outside forces on the merry-go-round?
Friction.
No, there's no
Friction? We're in physics. There's no friction.
I'm going to hold that.
We'll assume that it's a well-maintained merry-go-round with very little friction.
I'm gonna play that during the
No, don't.
Very, very dangerous.
Do not repeat this to your college professor or your boss and when you're a future engineer. Friction. Okay, now everybody, shh, listen up. Okay, so the girl walks to the edge. So there are outside forces on this merry-go-round. There's a force holding the merry-go-round up, right?
And the axis.
But it's at the axis, right?
Yeah.
So it's not doing anything. So there are forces between the girl and the merry-go-round. Friction, right? As she walks. But they're equal and opposite. We have the two objects that are interacting, right? Okay, so we should have conservation of angular momentum. So the question is how much before and how much after? How do we write that? How many objects do we have?
2.
So we've got angular momentum for the girl plus angular momentum for the merry-go-round before. And then we have angular momentum for the girl plus angular momentum for the merry-go-round after.
What is
Okay.
the merry-go-round do the same on both?
Okay, hang on. What makes up angular momentum? I erased it over here. It's I omega, or it's R cross MV, right? Okay, so for the girl, which one do we use?
Let's use
R cross MV.
Let's use R cross MV. What's her radius to begin with?
0.
0. So for the girl to begin with, she has no angular momentum. Now in the real world, she takes up space, right? All of her mass is not on the axis. But we'll assume that my daughter is quite thin and standing right there on the axis.
And very tall.
It says right, she's
very
extremely
tall.
dense. And tall. There we go. All right, which one do we use for the merry-go-round?
The first one.
I omega. I omega. Because it's a disk. So what do we put in for I?
What? Hold on.
1/2.
1/2
MR squared.
Let me control my movement.
1/2 mr squared. So don't forget that. We're going way back. 1/2 mr squared omega.
Here you go. Omega.
So we know m, we know r, we know omega to start, so we're in good shape. Okay, for the afterwards, what do we use for the girl?
RMV.
RMV.
Yes.
Okay. So we know her radius, we know her mass, and we know v. Do we have to worry about the cross product, or are we okay?
We're all right.
Why do we not have to worry about the cross product?
They're perpendicular.
Because the radius is out this way, but she's going this way, right? Perpendicular, so the sine of 90 is 1. So our cross product goes away. It just becomes RMV. That's nice. And for, this is I omega afterwards. So afterwards, this is 1/2 mr squared omega final. Uh-oh. RMV. Uh-oh. I got V and I got omega. How do I reconcile the two?
Wait. Oh, wait, so we really don't know.
Yeah,
Do we know V?
not right now.
How do we find V?
Because you just said we
Equals
didn't know.
omega R.
Okay, how is V and omega related?
They're, one's angular, one's
That is true. I will grant you that. But what's the connector? Connector is R, and so I want to get omega. Because I have omegas everywhere else.
Bye by R. Equals
So it'll be V will be,
omega.
omega.
Omega R.
okay, what's V over R? Omega. That's omega, but I want to get rid of the V, so V is omega R.
Yes.
So I put in omega R here.
No. It's R squared.
R squared, what?
Well, but it
Omega.
would give omega R.
Ah. So
So
look,
they cancel out. I told you they did.
So she is a hoop.
does the R go away? No, we end up with R squared. Wait a minute. This is mr squared omega.
That's just a moment of
Which is-
omega.
I omega, which it should be, right? Which it, she is a hoop.
all of her weight is.
Oh my gosh.
It could be a hole in her head or a very large nose.
Or a very large nose. Wait, I don't think
Spaghetti
Wait, she also has a cylindrical body.
She does have a nice cylindrical body, right? Alright, so there we go. Wait a minute. This is omega 2, right? Now, since we have to put in the radius at which she's at, correct? and the radius she's going to be at is going to be 2 meters. And this omega at the end will be the same as that omega at the end, right? So now we have everything we need. Do you see how you put different parts together? That you can have some pieces that are lumpy masses and some pieces that are continuous masses, all in the same problem. Okay? So from here on out, it's just math. So let's math it. So this becomes 100. This becomes 2 squared. This becomes 2. This becomes 2 squared. Her mass is 50 omega 2 plus 1/2 100 2 squared omega 2. There you go. The rest is just math, right? So let me just give you the answer. I trust that your algebra is sufficient enough to get you this one.
Wow.
Really?
I know, it's leap, but I get an answer of 1 radian per second.
That's what I got.
Yes.
That's okay.
400 divided by...
That's what my answer sheet got. 1 radian per second. Now, in the first problem, where we had the disk falling on the other disk, we said that it was a completely inelastic collision, right?
Yes.
And therefore it lost kinetic energy. In this case, do you think we lost or gained kinetic energy?
Let's say loss. Just to be
No.
safe. Wait, we gained?
I say it's the same.
I'm gonna gain.
We gained.
You're gonna get
Here's the
I'm
deal.
so angry.
When the girl walks across,
Gained.
is there a force that does work?
Yes.
The force of friction between her feet and the merry-go-round. Okay. Now the question is does it do positive work or negative work? When she walks outward, does it take effort for her to walk outward, or does she naturally walk outward? Have you ever been on a merry-go-round?
Yes. No.
Is it easy to walk outward?
No.
So easy.
It is easy.
It is easy.
Compared to walking inward.
It's easy.
Oh, yeah.
Walking inward, you're walking, right?
Walking outward, you fly out.
Oh. I thought it should be because you don't want to like fly off the merry-go-round, so you have to like pull back.
I got thrown off the merry-go-round once.
It's not effort.
I threw my grandma off the merry-go-round.
Against the rotation? If she walked against the rotation, what would happen is that if she walks
That is my
opposite to the direction it's rotating, that would slow it down and speed her up. If she walks in the direction that the thing's rotating,
I got stupid and be like,
it would speed up, but she'd speed up in the opposite direction.
She speeds up either way.
If it goes, yes, okay. If it goes this way, and she's on the rim and it's going this way, and she walks that way, what's going to happen is the disc is going to,
Slow down.
the disc is trying to go this way, but she's putting a force on it, making herself go this way, so the disc slows down, she speeds up in that direction. Okay? So the angular momentum of the disc gets smaller, but her angular momentum gets bigger, so they add up to the same value. Okay, now what if it's going this way? Here.
Shouldn't you like walk with it?
So here we are. Let's say it's rotating that way, and here she is, and she walks that way.
Okay.
She walks that way. Her angular momentum for the girl goes up. The angular momentum for the disc goes down. They add up to be the same as before. Okay, now what if you do the opposite? What if the disc is rotating this way, but she walks that way? Now what happens is notice that the angular momentum of the disc will get larger. But she will also...
Do you mean angular momentum?
Daggum. I'm right in the eye. Sorry. Sorry, everybody. Angular momentum, angular momentum, angular momentum. Okay. So the disc gets less, hers gets more, but they're both pointing in the same direction. This is the key. Unless she can walk fast enough to completely stop this thing. Right?
We should solve for that.
We could.
rocket ship.
You know, we could solve for it real easy.
Okay.
Her angular velocity would have to be 2. Because, see, since this has a 1/2 mr² but twice the mass, That's why we ended up with just reducing the angular velocity by 2, or by cutting it in half. So she would have to run that way at an angular velocity of 2, and that's 2 times 2 radius, so she'd run at 4 meters per second. So if she could run 4 meters per second that way, she would be running around, and the disc would stop. And then as soon as she stops, what will happen? The disc will speed back up to 2. Whoa!
What would be the opposite direction?
Be like running.
It'll keep going the same direction because the
You have to like
angular
jump
angular
off.
momentum
So you
remains
can like save yourself.
unchanged. Conservative. Okay, now look. What happens if the disc is going this way, but she runs that way?
This speeds up.
The disc speeds up this way, making the angular momentum here get larger, but she now is moving, and she gets an angular momentum, right? But she's going this way. She's getting an angular momentum in the opposite direction. So what happens is the girl gets an angular momentum that increases, but it's a negative.
Wait.
So it stays.
So it all stays the same.
No, wait. Doesn't she slow down?
No.
She would have to.
Yeah. Actually, what happens is that once she gets out there, yes, what she'll happen is she'll slow down. Hang on. She'll slow down because she's already going around this way. That's correct. Now, if she runs fast enough, she can make herself get a negative angular momentum, but the other one will get a much larger positive, so it all comes out in the wash.
Yeah.
Does that make sense?
Yes.
Okay. All right. Now, the key thing here is the kinetic energy can change, okay, in these collisions. It depends on whether the person's doing positive work or negative work as they walk, or whether some potential energy is being decreased. Okay, so like for instance, ice skaters spinning around right at the end of their program, and then they do the death spiral, where they bring their arms in and they spin so fast you can barely see what's going on, right? They turn to a blur. Okay, the deal is this, is their angular momentum remains constant. They're not doing this with their foot to make themselves go faster. Okay? What are they doing? They're pulling their arms in. Pulling their arms in takes effort.
Oh, it's so difficult.
It's very hard, and it takes work, and they're doing work with their arms. The work with their arms is increasing their kinetic energy, but the angular momentum is remaining constant. Okay? Now, what if they take their arms and let them out? Okay, does that take work? No, because their arms are just naturally flying outward, right? Their arms naturally fly outward. Negative work's being done. And they slow down. But the angular momentum is the same. So the kinetic energy can change in a collision, but the angular momentum will stay the same as long as there's no net outside forces. Yeah.
So are you saying, like, let's say the skater, like, they turn in or whatever, and then after a while they let themselves out, but they pull themselves back in. So are you saying, like, they could keep on going on like that forever?
In theory, if there's no friction, then what will happen is they speed up, slow down, speed up, slow down, in between, slow down.
I'm sure they do
Okay?
all the time. Yeah.
All right? Now, we can do that. Yeah, sort of. Let's see, does this one work good? This one's not too bad. All right, I need a volunteer.
Ooh, me. Alex, you still haven't done your backflip.
Come on, Gia, we'll try it.
Ain't no thing. She might fly off the chair.
She might fly off the chair. Actually, you're perfect because we can take your shawl and tie you in,
Okay,
so you
good.
won't fall off. Okay?
Are you really going to?
Safety.
That's not.
You're in like a
Now, when I say tie you in, I mean tie you in. Here you go. That's all right. Okay, one in each hand. All right, now put them outward.
Oh,
All right, ready? Okay, now pull them in. Not the greatest, but you just see her speed up? We got a lot of friction going on here.
Try that one because it doesn't lean back and stuff.
That one doesn't lean back? All right, don't lean back. Now pull your arms in. Can you do it? See how she speeds up, but then friction takes over, so it kind of slows you down. Let's try this chair. This one has more possibilities of you falling out.
You'll be alright. Someone's gonna get hit in the head with a book.
Hey! Look, the chair has an instruction manual.
Yes, we all move up a little.
It says don't do this in physics. All right, ready?
Yes.
All the way out. All right, ready?
Yeah.
Okay, pull them in. Can you do it?
I'm sorry.
Can you speed up a little bit? All right. Now, if there was no friction, she'd speed up and slow down, speed up and slow down. Right?
Ain't no friction.
All right. Let's try. We need somebody here. Alex, come here. You got long arms.
Okay, I see how this.
Yeah? We'll have a bigger change that way.
You got a turntable.
Maybe you should like.
Do you? Where?
Oh.
Aha!
Do the one with the.
Sit on that.
Oh.
You're gonna die.
Alex, you're going to I see you being
Oh, goodness gracious.
Oh, yeah. You got it? There we go. We had one of these in my college. What they did is they had a bar stool with a back. They had mounted like a pilot seat in it, and they had a 5-point harness so you could strap yourself in. And then they had a little motor on the bottom, a little electric motor that would speed you up and spin you really fast. And then you had weights, and you could get those weights about this far in. You couldn't pull them any farther because you were going so fast. And then everybody ran because half the time you let go of your weights. Try it again?
Well, that's like when you squeeze your stomach and then you can stay on.
Yeah.
Alex,
Yeah.
spot.
Right,
Use
ready?
your abdominals. No, don't spot because then you lose.
Oh, you're doing the other way. Slowing down.
Loser.
Ready?
You're not doing any work. Whatever.
Oh.
What? You proud?
All right, wait.
Wait, no,
Alex, you try. Yeah.
you want us to spin you?
This is how astronauts turn in space, by the way.
Really?
I bet they have like
Because in
crazy
space,
obliques. Oh my God.
are there any outside torques?
No. So,
You're floating there. How do you turn around? And you can't turn. So how do you turn? You do this. Okay.
I bet they have crazy obliques. Oh my gosh.
What they do is they put their arms out, and then they twist. And as I twist, notice that my upper body goes one way, and my lower body goes the opposite, right? And I'm back to where I began, right? That's what happens in space.
Have you ever
Oh,
been in space?
sure.
We exist in space all the time.
That's right. I'm in space right now. But if I wanted myself to turn, what I do is I go like that. Notice my lower body turns more than my upper body, right? And then I lower them.
You would be your car like.
You'd be a great like exercise instructor.
There you go. And that's how you turn in space. By the way, this is how a cat.
Crazy oblique.
That's right.
Yeah.
Abs of steel. Wow. Go ahead.
you saw a cat?
All right. How many of you have a cat? Okay. Okay, take your cat, grab your cat by the legs, flip them over,
Oh my gosh, this one my cat.
and then hold them like this high, and then let go. All right? Your cat will land on the ground, paws down. How can they turn themselves? They do exactly what I did. They go, huh? Actually, that's what they do. If you, they videoed it, and when they video it, what happens is the first thing they do is they spread their back legs out as far as possible, and they keep their front paws in, and they twist their upper body down towards the ground. And then they're twisted around like this, right? So then they do the opposite. They put their front paws out, and they twist their lower body around.
Like 2 seconds.
Yes, and you can do it like from this height, and they'll still do it. It's crazy. All right, here we go. Okay, what about this one? Now we have a 40-kilogram boy running this way, runs,
Oh my gosh.
and No, my son will be more than that. And jumps right on here.
They fall on
He
their
slipped
face.
like on American Spanish Home videos.
Boy runs at 3 meters per second, jumps on a stationary merry-go-round. I want to know how fast will the merry-go-round be going?
Falls on his face.
The merry-go-round has a mass of 100, and the radius is still 2 meters.
Why is that boy less than your daughter?
I don't
Is
know.
it your son?
Actually, I just made these up. Come on, I want you to figure out how fast will it be going. Go.
Slow.
Wait, is this one conservation of?
And it's gonna be going.
Yes, conservation of, is it conservation of angular momentum?
You said yes, so yes.
Is there an outside force on the merry-go-round? Sure, at its axis, right? But will it produce an outside torque? No, because it's at the axis, right? So when the boy jumps on the merry-go-round, the whole thing won't take off this way, right?
Right.
It'd be really dangerous.
It would be dangerous. A small boy jumping on a very large hockey puck. That's what would happen. In fact, you can do that one next. That's an awesome idea. All right?
Wait. For the first one, since it's stationary, then there's no angular momentum.
Yeah, so it's
Now, wait a minute. We cannot do this, right? Because there's an outside force on the axis, keeping the the merry-go-round from moving, right? However, we can do this because that outside force does not keep the merry-go-round from rotating, right? It's free to rotate, but not free to move. Okay, so how many objects do we have before?
Two.
We have the boy, and we have the hockey puck.
and now
And afterwards, we have the boy
Merry-go-round.
and the merry-go-round. Now, here's the deal, though. Is there an angular momentum for the merry-go-round to start?
No.
No. Is there angular momentum for the boy at the beginning?
No.
Yes.
Who said yes? Yay!
Right?
There is angular momentum for the boy.
Then you would need to know how far away from the axis he is.
There's an
We sure
RMV.
do. Right there, that's 2 meters.
What?
Well, I think about it at the, like, right before he jumps on, he's R and V, like, he's on top.
Yeah, here's the deal. Right before the boy jumps on, he has a radius of 2, has a mass of 40, and a velocity of 3, right?
Oh, so we don't even know about the
Because it's right.
Now, what if we're looking at it from the top, the way I have it is the boy runs like this and jumps on, okay? Now, if the boy jumped on like this instead, this way will cause the merry-go-round to turn, right? But what if the boy ran this way, straight towards the axis and jumped on? Would that make the merry-go-round turn?
He's gonna hit his head on the bar.
The answer is no, because the boy has no angular momentum to start.
He's no radius.
Because there's no radius. The key thing is you're looking at the effective radius. Here's the effective radius, 2 meters. Here's the effective radius here, no meters. He's right along the radius, right? Does that make sense? There's no, here's the radius in each case. But this one has, it's right along, so the cross product gives you nothing. Because the angle is 180, right? Okay, so here we go, everybody. Come on. I see a lot of you sitting there but not doing anything. It's not going to do you much good when the test rolls around. So this is RMV equals RMV plus I omega.
Okay.
Right?
Yes.
Beforehand, this is 2. The mass is 40. The velocity is 3. The radius is still 2. The mass is still 40. The velocity afterwards is, I don't know.
It's omega over.
This is 1/2 mr squared omega. Now we have a velocity and we have an omega. The m of the mass of the merry-go-round we know to be 100. The radius of the merry-go-round is 2 squared, so that's 1/2. But we have this omega thing here, right? Omega and v. So we either have to change this to v or this to omega. One of the two.
What are we solving?
I got it.
Good question. I think I'm asking for omega.
Well, then let's check.
So let's change this to omega r. Okay, and if you do that, then you can solve it. Now I can keep this one as V because the units come out over here.
Isn't it 2 squared? Oh yeah, never mind.
Yeah, I got a 2 squared here. Sorry, it's kind of small. This looks like an N here too. All right, and you get an omega final. Will the omega afterwards, will it be more or less than, let's see, omega equals V over R, right? Will it be greater than this or less than that?
It's less.
Less, because that's the original omega of the boy, right? Right when he jumps on. Okay? And it has to be less than that because we're picking up mass, right? We're picking up rotational mass. So it has to be less. What does it turn out to be?
The inverse.
Yeah.
Yeah, it turns out to be 2/3. 0.67 rads per second. There you go. Very radical. Okay, by the way, that turns out to be your problem number, I think that's number 6 in your e-homework. Is that essentially that problem where like a lump of clay or something is thrown against the edge of a wheel or something and the wheel starts to turn, I think is what it is. Okay? So that's that problem exactly. Okay. All right. What about this? Let me see if I can draw this adequately.
Ben, why does it give you time?
Wait, how did you?
I took a Thanksgiving break.
Is there a hole in the
Me
table?
too. Hi. Except it was like
You went to
capital
college. That doesn't
B-R-E-A-K.
All right, we have a table. There's a hole in the middle of the table. There's a ball on the end of a string
Oh, wow.
attached to
Science
it.
place.
This looks familiar.
On the other string?
Okay?
Is there a weight on the end of the other
There's
This is
there's
really
a mass
familiar.
right here. Okay? And right here, you can pull it downward or upward to change the radius. Okay? All right, so it's moving right now at V1. As it goes around, you're going to pull it inward so that it ends up over here, moving at a velocity of V2. So you're going to pull it inward with tension. This is radius number 1, and this is radius number 2. Okay, so V1, radius 1, V2, radius 2. Okay, so my question is how does V2 compare to V1?
Don't they have the same angular momentum?
Will they have the same angular momentum? Is there an outside force? Tension. But does the tension produce any torque?
No.
No, it's along the radius. So can we use conservation of angular momentum?
I'm going to.
Yeah. L1 equals L2. Okay. I omega, RMV.
Wait, is it a sphere or a?
This is a small lumpy mass.
Let's do R and B.
R cross MV1 equals R cross MV2. Do we have to worry about the cross product? We're at 90 degrees, right? So that goes away. Does the mass go away? So my velocity 2 just equals R1B1 over R2. Notice that if R2 is smaller, the velocity goes up. If R2 is larger, the velocity goes down. Okay? All right, now we write an equation. Tell me what the tension is going to be.
Boo.
No.
Boo.
Is this a forces thing?
Tension would be a forces thing, right? So we're not talking energy. We're probably not talking momentum or impulse of any kind, right? Because we don't know the time, right? It's not kinematics, so therefore it's going to be forces.
And it's circular motion.
Ah, bingo.
I'm so happy for you.
Equals MAC, because we have circular motion. What is the force causing the circular motion? Tension.
And that's not too difficult.
And what's AC?
But don't I?
We already have B squared.
But.
Yeah.
B's and R's, right?
It'd be
Does that matter?
B2.
M2 times the quantity v squared over r1.
Blah,
All right.
blah, blah.
If this is our V that we're getting to, right, what tension is required to pull it from here to here? This is the V we're interested in, right?
Yes.
V2.
And the radius we're interested in?
R2.
It's r1 minus.
And the radius we'd be interested
is
in
at
would
that
be,
point, right? So it's
R2.
R2.
that would be R2 as well, right?
Yeah. So we plug everything in.
So, we would plug this in as, to get it to R2, then we would be at velocity 2, which is R1 V1 over R2 squared all over R2, right? So we end up with our tension being M R1 squared V1 squared over R2 to the third power.
Wait,
That's our tension.
no.
That's right. Algebraic.
Why to the third power?
Because divide R squared divided by by R2 squared divided by R2 gives you R2 cubed.
Oh, I got it.
Got it?
Not as pretty.
All right. Now, let's calculate the work that was done to pull it from R1 to R2.
Force times.
Tension.
Force times distance. But, whoa,
Oh, I have a changing.
this changes, right?
Yeah.
With radius.
So I won't do that.
We can.
Can I do change in kinetic energy?
You could do change in kinetic energy.
Can I say change in angular
Angular momentum.
yeah.
Okay, there would be two ways to do this. Now we're trying to figure out the work to go from here to here. So look what I'm going to do to change this. This now becomes some random radius, right? I'm starting from here, and now I'm going through a bunch of radii, right?
Yes.
Does that make sense? Because the force is not going to be the same. The tension won't be the same at each radius, right?
Yes. Oh, wait. Yeah.
Notice as the radius decreases, the tension goes up. Oh, we have an integration going on here. Boo! 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 Down with integration. Now, here we go. What's work? Work equals integral F dot dr, right?
Okay.
Oh, come on, don't be afraid. This will show up on the exam somewhere.
A lot of those are.
What are we going to? From R1 to R2, right?
Yes.
What's our force? Our force is M R1 squared V1 squared over R cubed integral R1 to R2 dr.
A lot of those are
Isn't
constants.
it r2 cubed?
No, that's. No, we said
No,
it was
we
gonna be
changed it
random.
because we're going from here all the way to here. So we're starting at R1 and ending at R2. So we're starting at this radius and ending at that radius. So I'm leaving it, instead of it being exactly what the tension is at this spot, I've made this so that this is the tension anywhere. Okay? With these starting conditions. That starting radius with that starting velocity. Okay? All right, we got a bunch of constants.
Yeah.
M R1 squared V1 squared integral R1 to R2 dr over R cubed. You can do that, right?
Yeah.
It's not that big a deal.
My W's are looking like omegas now.
What is it? Anyone? Anyone?
What?
No, wait. -1.
Negative.
It's negative 1/2 R
I forgot how to do
over R squared, right?
Oh.
Is that right?
Yeah.
Because you add 1.
Or 1 over 2R.
Yeah, that's right.
Here, it's the same thing as integrating this, right?
Yeah.
So you add 1, divide by whatever that number is, right?
Yeah.
So this number, you add 1, it becomes negative 1/2. So you divide by,
It becomes negative.
2.
sorry, negative 2, and then you divide by negative 2, right?
Yes.
Yeah.
Okay. So you end up with this, but this is from R1 to R2, right? So I get negative M R1 squared V1 squared over 2. Put all that together. And then I end up with 1 over R2 squared minus 1 over R1 squared. There you go.
Man.
And it looks like I'm going to end up with a negative number.
Yikes. That's a weird equation.
Did it take work for me to do this? Pull this inward?
Did it ever?
Takes effort to pull that thing in, right? So what happens though? Notice that R2 is smaller than R1, right? So that makes this number bigger than that number. So the negative will cancel with that negative. So if you want, you can swap this around. Get rid of that negative
No, stop.
and do this.
Boo.
There we go. Now we're done. Okay?
I like it.
I don't care.
Told.
That should work.
She got told.
Now, there was the suggestion that, wait a minute, that's a lot of effort. Doesn't work also equal the change in energy?
Seriously?
What kind of energy is changing?
That's okay.
There's no potential changing, right? Just kinetic? So wouldn't that be kinetic final minus kinetic initial? What kind of kinetic do we have? Now you could do this as rotational, or since we have a lumpy mass, you could just do the kinetic energy of the mass and its linear velocity, right? That would also work. That's actually going to be easier for us probably. So this is 1/2 mv squared final minus 1/2 mv squared initial.
Now he tells.
Yeah. Actually, it was told to me. This is not the way I work it. But it should work. So I get a 1/2 m v final squared minus v initial squared. Okay, what's our initial velocity?
What?
What's our initial velocity?
V1.
1/2 m. Our initial velocity is just v1 squared. What's our final velocity?
That.
R1, V1 over R2.
R1 v1 over R2 squared. I predict that equals that.
Me too.
I predict that too.
It should. Do we need to check?
It looks good. It looks good.
It looks good.
It looks nice,
Guys, you're a bunch of wimps.
I know.
but it's
You
okay.
have to tell everybody.
R1 squared v1 squared over R2 squared equals v1 squared. Okay, common denominator.
What?
95.
No, minus.
I was like,
You can take a V1 squared out, and then it's R, and then what you're left with is fraction mass that equals that.
Fraction mass that equals that.
R2 squared.
Multiply
Oh,
by
yeah,
R2
yeah.
squared over R2 squared. So I end up with R1 squared v1 squared minus v1 squared R2
I
squared
stopped it there.
over R2 squared.
Mr. Brown, what I would just do in that case, that second line, this, yeah, take out a V1 squared. And
It's all like her.
do you see, that's R1 squared over R2 squared minus 1, is what you had originally. And if you factor out an R1 squared,
Does it turn out to be the same thing?
yeah.
It should. It looks very different,
So, Mr.
but it
Brown,
should be the same thing. Yeah.
before you multiplied by R2 squared over R2 squared,
Yes?
you had,
This. Oh, no, this.
right, and then from there, if you factor out a V1 squared, you get an R1 squared over R2 squared minus 1. And then if you factor out an R1 squared, you get a 1 over R2 squared minus 1 over R1 squared.
That'll work. So it is the same thing. I like it. Okay, here you go. So remember, was positive work done? It took effort, right? Okay, whenever positive work is done, the kinetic energy will go up. Whenever negative work is done, the kinetic energy goes down, but the angular momentum still remains the same, right? Okay. Buddy, let's say we have this merry-go-round. The merry-go-round still has a radius of 2 meters. It still has a mass of 100 kilograms. Okay, this is important, everybody, because you're likely to see some problems like this. All right? And then we have our person, which was 40 kilograms, running this way at 3 meters per second. Okay. Now, when this thing was pinned down, we figured out that afterwards the final angular velocity, at least, was 2/3, right?
Yes.
Okay, but here's what we want to do this time. We're going to say that this is like a big hockey puck on an ice skating rink. It's free to move. Okay? The child is on ice skates. They skate up at 3 meters per second and they jump on. They jump on right here. Now, when they jump on right here, we have a collision.
The merry-go-round and rotate at the same time.
Now, this time, is there any outside forces at all?
No.
So, will this be conserved?
Yes.
Yes. Will this be conserved?
Yes.
Yes.
Yay.
Okay? Now, you're likely to see, you see some things on the test a lot of times, things like this. You'll see, there was a problem like this one time where you had like a meter stick floating on an air hockey table or like out in space, and a ball came and hit it and stuck to it. Okay? When the ball hits it and sticks to it, if the whole thing's free to move, this is true and this is true. Okay, what if it's an elastic collision and it hits and bounces back? Does it matter? Still no outside forces. This is true and this is true. Okay? Now, what if this thing is like a meter stick that's pinned? So it's hanging like this.
Then only that one's true, right?
Okay, which one's true now?
The rotation.
This one. Okay? Because there's an outside force, but it's right here at the pivot point. So therefore, this is no longer true, but this is still true. Okay? Does that make sense? Okay, so sometimes, actually a lot of times, angular momentum is true, conservation. But conservation of linear momentum is not true. Okay? Alright, so here we go. So let's look at this now. What does this equation tell us when it's all free to move? It tells us that mv plus mv before equals mv plus mv afterwards. How many of these objects are moving before?
One.
One. Just the kid. All right? Afterwards, both.
At the same.
But they're moving at the same speed, right? So it's going to be mv for the kid before equals m plus m v afterwards. And this is for the kid and for the big disk. Okay? And so let's figure that out. So mass before is 40, velocity is 3. Afterwards I got a mass of 140 and a velocity afterwards of unknown, right?
A lot.
So that's going to be what? 120 divided by 140, so it's going to be less than 1 meter per second.
0.8.
607.
0.8 what?
6.8.
Meters. 0.68? 0.86?
Let's find out.
0.86.
607.
Okay, now, excellent question now. Which way is that moving? The answer
That
is,
way.
Up and rotate.
what does this tell you? Does it tell you anything about this? It tells you only about this or this, right? So the center of mass before was moving which way? Up. So which way is the center of mass moving afterwards? Now, where is the center of mass?
A little to the
Ooh,
right.
that could be a question they'd ask you, right?
A little to the
The
right.
center of mass of this one's here. The center of mass of this one's obviously here. So the center of mass is going to be somewhere in between here, but closer to here, right?
Yeah.
The center of mass of the entire system is going to be along here, but closer to over here. And the center of mass of the system is moving up. Is the center of mass of the system moving up at 3 meters per second? Say no.
No.
It's not.
Because only part of the mass is moving, right? How do we figure out the velocity of the center of mass? The sum of the mv's over the sum of the m's, right? Just like we find out the center of mass location is the sum of the m r's over the sum of the m's, right? Actually, we did find the velocity of the center of mass before. Because it's going to be that, right? Because it doesn't change. The center of mass is velocity is 0.86 meters per second. Before and after. Never changing. Now, that tells us only about the linear nature of the object, right? Let's talk about the rotational nature.
It's so funny when he gets on his thing where he just jump on and stop.
What's that?
Did he like just jump on and just like stop his legs, or was he continuing to stop running?
No, he jumps on and goes.
Did he jump onto the outside?
Yeah, outside edge, right here.
But-
Sorry.
The
He
same way
stands
we
on
got
a pin as well.
What?
He stands on a pin as well. At the very edge.
Right.
No.
Of course. Okay. We had another question.
Oh.
You have a question?
Listen, how come you can't do the center of mass right before he jumps on? Like when he's at the
You can. The center of mass right before he jumps on is right here. The center of mass of the system continues to move upwards. All right, so what do we have here? How many objects? L plus L equals L plus L. But afterwards, they're connected, right? So I can put these together. L for the whole thing. Before and after. For the boy, it's R cross MV.
Yes.
For the merry-go-round or big hockey puck, it's 0 to start. So all we have before is just that for the boy. Does this look awful familiar? Isn't this the exact same thing we did before? Has anything changed?
No, because before the friction was
Yeah.
negligible too. So.
Did that fact that it was pivoted before and now it's free to move change anything about this problem?
No.
It's exactly the same as before. So we end up with R cross MV for the boy afterwards, plus an I omega for the big thing afterwards. And we ended up with omega being, what was it, 0.67, is that right? Rads per second. Notice that that doesn't change. So what happens is the boy jumps on, the whole thing moves up, but as it moves up, what's it doing? It's rotating. Where's it rotating about?
The center of mass.
The center of mass, which will be somewhere in here now, right?
Oh, that's
So the thing will be wobbling as it goes up.
Because I was going to say, if he's moving and it's, if it just pivot at the center of mass would be moving.
Right.
But the center of mass goes
So it's going to free rotate about the center of mass instead of the fixed pivot point. Oh! So does it change?
Yeah, wouldn't it have to?
Drat. Now look what changes.
Oh, the radius from the
Do you catch it?
Yeah.
What changes?
the radius.
Okay, before, it's like, how could it be exactly the same, right? Because before what happened is the boy ran up here and it pivots about this point, right? But now the boy jumps on it and the pivot is no longer there. Where's the pivot?
So right there.
Right there. So we have to come up with a new...
No.
Oh, this changes.
No.
Yes.
And this boy would be like, at some points moving
We
really
have a
fast.
new radius for the boy,
Touching it on.
and we have a new moment of inertia.
Wait, you can't.
Sure we can.
Oh wait, oh yeah, because you can move.
All right, let's do this. Let's do this all in one fell swoop, everybody. Let's just do I omega for the boy plus the disk. Here's how we do it. Here's how we do it. Here's our new device. Our new device is this. There's the center, but here's our center of mass.
Bless you. Bless you.
Okay? Let's find out the moment of inertia of this entire object, because that's a legitimate question they could ask you on the exam. So, first of all, let's find out, we need to find out where the center of mass is. So let's do that math. Over here. Where are we figuring it from? Let's figure it from the geometric center.
Okay.
Let's figure it from this point, this point right here. Okay? All right, what's the mass of the disk?
100.
What's the radius of the disk to that point?
Wait, what point?
I thought.
Do we know?
The knees?
Can we figure out where the center of mass is?
Yeah, we can use the X and solve.
Oh yeah, we know the location of the center of mass. Okay, here we go. Here's the center of mass for the disk. Here's the center of mass for the boy. We're going to use this as our location point, where we're measuring from. Okay? So the radius for this is 0. Plus the mass of the boy, which is 40. And what's his radius? 2. Okay, what's the mass of the whole thing?
140.
140. So what's 80 divided by 140?
What's 8 divided by 14?
Okay, smarty pants. What's 8 divided by 14? Oh yeah? What's 4 divided by 7?
4 divided by 7 is 4 7.
4 7. Work with me. What is it?
0.57.
0.57. Okay, everybody. So here's our center of mass. 0.57 meters. Okay, now let's figure out our new moment of inertia about that point.
Okay, so
Shouldn't be that hard. Okay, so our moment of inertia for the whole thing consists of the moment of inertia of the disk plus the moment of inertia of the boy. Okay, so the disk is going to be 1/2 mr squared
plus mr squared.
plus and md squared, right?
For
The parallel axis theorem.
yeah.
So that's going to be m, and our d is going to be 0.57 squared, right?
Yes.
Plus the boy. The boy is now mr squared, right?
Yes.
mr squared. What's the radius for the boy?
2 minus.
2 minus 0.57, which is 1.43, right?
Sure.
All I'm hearing is
Okay, now look.
Voila.
Oh, this math thing.
This is the parallel axis theorem. The original plus how far we moved it.
Just saying.
The original plus how far we moved it. Right?
Yes.
Remember the parallel axis theorem?
Yes.
Okay, and then the boy is just a lumpy mass, right? So his mass times his radius squared. The radius squared for the boy, though, is this. 1.43 meters. Right? So now we got to plug in all that crap stuff. Right?
I'm getting 314.
314?
Sorry. 314.
I don't believe you.
Oh, that's
No, 3.14.
I tried.
0.5
Hi, back
times
one.
100 times
I get 3 squared equals.
I was going
plus 100 times 0.57 squared. Okay. Plus 40 times 1.43 squared. I get 314.
Man, it's pi. It's 100 pi.
That's awesome.
Kilograms meters squared.
It's 100 pi.
Okay, so where were we?
Oh, we were saying right there, that equation.
Okay, angular momentum. L1 equals L2. All we had before was RMV for the boy.
The boy.
All we have afterwards is I omega for the whole thing.
Oh, not the other problem.
Right?
For this problem.
Now, careful everyone. RMV. RMV.
Finding omega.
Mass of the boy is easy.
This one is
Velocity of the boy is easy.
Is it 1.43?
What's the radius of the boy?
1.43.
Very good. 1.43. Because the boy is running up this way, and there's the radius to the center of mass, the rotation point, 1.43.
It's different from this problem.
This is 314 kilogram meters squared, and then we find omega.
So that changes the center.
Yikes, so what is that?
0.55
Omega equals 0.55
rad per second.
rads per second. Now, everyone, let's do a little idiot check here.
It's less than 0.67.
Okay, now look. Before, when the boy jumped on the merry-go-round couldn't move. We got an angular velocity of 0.67. now we end up with an angular velocity of 0.55. Does that make sense that it should be less?
Yes.
Yes.
Why?
Some of the kinetic energy is.
Okay, we're not talking kinetic energy.
As you move out,
Sum of the momentum yes. Sum of the momentum before is now taken up with the fact that the whole thing's rotating, right?
Yes.
Because our moment of inertia has increased from before, right? We have a larger moment of inertia now than we had before. So the angular momentum at the end has stayed the same. It's just that now we have a larger moment of inertia, therefore the angular velocity has decreased. Hey, how we doing? Did your brain hurt?
Yes.
Yeah, I was fine until this last problem.
This